All right, so today we're going to be talking about the volume of a bagel. Bagels are known for their distinctive shape and general deliciousness. A bagel, mathematically known as a torus, is round, but it can't be considered a sphere or a cylinder. It's neither. So our volume formulas from geometry are not going to help us. Today we're going to do another food lab, sort of, for calculating the volume. So here we have my beautiful bagel. And we know, we could use water displacement, but I wouldn't want to put my bagel in water. Unlike the pear, where that'd be fine, it would just get clean. This would fall apart. If I put it into water, it would be bad. I won't put this in water. But I could cut it into smaller shapes and figure out, what was happening. I could do that. It is a pre-cut bagel, so, that's the kind I can find at the store. So, it is what it is, but I could cut it. But how is it different than what I did with my pear? So with my pear, there was middle. This is missing a middle. So as I'm thinking about this, I could use water displacement, but then I wouldn't want to eat my bagel. And it really wouldn't work because water would get absorbed into the bagel. And so, not a great method. Porous, meaning that it'll soak up the water. Whereas the pear will not soak up water. Or I could cut into okay. So it's similar to the pear. As circles seem to be involved. But the whole okay. Cut your bagel in half crosswise, not how you slice it to put cream cheese on it. So, like so. This, of course, is a different bagel, but, same difference. It'll do fine. Like this. Okay. Take 1/2 and center it on the y-axis, like so. So let me move this up. And so we want to center it. As you can see, I want center, like so. Okay. Trace the part of the bagel that is above the x-axis onto the coordinate grid. Okay. Okay, there it is. What would I have to do to this to get a bagel? Well, I would rotate it around the x-axis to get a bagel, right? And this circular, the donut-like bagel shape would come out, right? We'd end up with another circle-like thing down here which would go from just before 2, -2, out to 6 wide, not quite too wide, out to 6. Right, we'd get that the bottom part of the bagel would be there now. So that like I could line it back up, right? Either way. Pretend I did a better job with my bagel. But, and then I'd get that bagel connection. Like the tube would come out of it. Right? It's weird, it's hard to draw. Okay. We would rotate. Okay. All right. Now that we have a graphical representation of our bagel, let's go back to finding the volume. Since our formulas don't work, let's use our slicing technique. Using a whole bagel, slice the bagel lengthwise into as many slices as you can. Are the slices identical? Why or why not? So I've taken a bagel and sliced it like so. Are the slices identical? Best I could do was 4, which works because that's how many there were. I suppose if I had a better tool, I could slice it a little bit better. The slices are more similar than they were with the pear. As you can see, they're definitely more similar because it's not, oh wow, I'm making a mess. They're more similar, but not quite the same. Sorry. Okay. So we've got our slices. Geometry won't work. The slices are identical, not quite. No. Some are a little smaller. Okay. Unlike the pear where we had very big differences, we have very small differences here. Okay. They're not the same. They're close, but they're not the same. Okay. How would you describe the shape of the slice? Well, it's a circle with a hole in it. I hope you are noticing that. It's a circle with a hole. And now my middle hole is very trapezoidal, this particular bagel. Some of them look really triangular as you cut them, but it's what bagels do. We're going to pretend it's a circle inside instead. So I think if I'd used a whole bagel, that would be more circular than it is here on the smaller bagel. Bagels are made differently than donuts, where they actually use a cutter and the donut, that is a clear circle. But then I won't eat it as quickly, And it also made more sense to talk about the cream cheese and all that stuff with the first cut that we made. All right, use a ruler to measure the following dimensions. We want to be in centimeters, then calculate the volume of each slice. So I'm going to take the bottom slice. We'll start with the bottom. We'll do that one together. And so we'll call it slice number 1, 2, 3, and 4. So the radius of the outer slice. So I'm going from corner to corner, and I got 9 and a half. And I need to cut that number in half. My diameter is 9 and a half, which means my radius is 4.5. Half of half is a quarter. So big R is 4.75 centimeters. Looking at the inside and pretending it's a perfect circle, even though it's not. Even though we know it's a trapezoid, we're pretending it's a circle. And it's a circle with a diameter of about 2.5, which makes little r 2.5 cut in half is 1 and 0.25. The thickness of the slice, I can't see what I'm doing. Looks like it's a 0.5 centimeter thick. Okay, and then to do the volume, it's going to be a cylinder, right? Anyway. All right, so the volume will be pi big R squared minus pi little r squared times the height. Okay? Or pi times r squared minus little r squared h. So that's what we're going to do as we do these calculations. So this will be pi 4.75 squared minus 1.25 squared times 0.5. The zero there. Well, the math, I'm going to do all the other measurements, and I'll be back in a second. Go ahead and write that down so you can figure through it. It makes sense to you. As you can see, the outer radius changed very slightly, and it got smaller. I started from the bottom and went to the top, so it was a choice. The inner radius also changed slightly. The thickness of my slice, I actually did a pretty good job. They were fairly even. And so, notice they're all just in terms of pi. Pi just kind of sits there. Nice shut the pi here at the bottom. Because it's circular, I spun it. Pi comes from spinning it, because that's what's making it circular, is this rotation. Okay? Number 6, excuse me. Use a green colored pencil to outline the region that determines the outer radius. I'll use my green pen. So outer radius, we want to mark in green, and inner radius, we're going to mark in blue. Those colors are really close, so let's go back here. We're going to look at this, ignoring this. My outer radius is from my axis of rotation up here. Top part of the curve, that's going to be R. And then little r will actually be down here. The hole. Big R is the edge, little r is the hole. Okay. All right. Let's call the green curve r of x and the blue curve little r of x. Write an interval expression that will give me the exact volume. So volume will equal pi times the interval from Give me a minute. All right, I'm going to need to look at my picture to figure out what my things are. And so x, I'm going to go ahead and use -2 and +2 because, you know, maybe my bagel's thicker or whatever. -2, +2. Okay. Then I'm going to take the green curve, r of x, And I do need to square that. And that would have been if there was no hole. I would just put dx at the end, I'd be done. But there is a hole in the middle of my space, so I need to subtract the volume of the hole, little r of x, squared as well. And so I make sure to group that together, dx. Where these are the x, the boundaries on x. The left and right. Okay. This radius, use capital R. This is if you will. And then dx, of course, is the width, height of each thickness. Okay, this is called a washer. So let's just really quickly, before we get any crazier, when there's a hole in the middle, we're talking about a washer. Okay, and so big R is from there and little r is right there. Okay, so this is known as the washer method, and that's that. Let's take a look at our box. To use the washer method, there's a space or gap between the region and the axis of revolution. So sometimes there's just a nice thing, but then I'm like the curve, and like where I'm like I might be creating a gap myself, which is a little interesting. Like if it's bound, let's say by the x-axis, this one is bound by this, but I rotate around something else to create the gap. But big R is from wherever the axis of revolution out, and little r bottom of the curve, which shows a space. Draw sample radii from axis of revolution to boundaries of region. Write expression for big R and little r. Think upper, lower, or further right, closer. Set up interval. Pi just sits there. So either in terms of x, if I'm rotating around a horizontal axis of rotation, and then dy if I'm rotating around a vertical axis of rotation. Okay. And we'll talk more in just a minute. Have a great time.